Yeah.
Hello, thank you very much for having me. So my name is Valia Mitsou. I'm a finishing PhD student at the City University of New York. And this last year of my PhD I'm spending in Japan, in Kyoto University, as a visiting researcher there. And today I'm going to talk about a very cute game, a card game which is called Set. I think some of you already know. I know that you know it. I'm very happy about it. And this is joint work done with Michael Lampis, who's sitting there. So let's start. This, as I said, is a card game. So you have a bunch of cards that have some figures, some shapes, as you can see. And you deal some cards. The game is you deal some cards, and you're seeking a set of cards that match in a certain way, as I'm going to explain. But first of all, let me describe the cards. So each card has a number of colored shaded symbols, as you can see. So the symbols can be oval, diamond, or this weird S, which is called a squiggle. Then the color can be red, green, or purple. I hope no colorblind people are here today. This will be very bad. The shading can be blank, striped, or filled. And the number is 1, 2, or 3. 1, 2, or 3 items can be in each card. And so as you can see, a card looks like this. So this particular one has 3 symbols, 3 squiggles in particular, that are green and solid. And since there are 4 different properties, 4 different attributes, and for each attribute we have 3 values, and there are 3 to the 4 total cards. Okay, 1 for each combination of values. And now the game is as follows. You need to find 3 cards that match in a way that either for all properties, for all attributes, either they all have the same values or they are all different. So what does that mean exactly? That, for example, these 3 cards constitute a set. Why? Because they all have the same color, they are all red. They all have the same symbols, all oval. They all have the same number of symbols, so 2, 2, and 2. But they all have different shading. So this is open, this is striped, and this is solid. Okay. Another set. This is also a set. Now all 3 cards have same shadings. They are all striped. But for all other properties, the values are all different. So this is green, purple, and red. This is 1, 2, and 3. And this is squiggle, oval, and diamond. Okay. This is a bit harder set. This is even harder. So these are the ones that are most hard to find, I think. So this is for all attributes, all properties are different. Okay, so yes, they all have different colors, all different symbols, all different numbers, and all different shadings. Oops. And this is not a set. And why is this not a set? It looks like a set in the beginning. So they are all red. They are all different shadings. So this is open, this is striped, this is solid. And they all have different symbols. So these properties are okay. But the problem is with the number. So these 2 cards have only 1 symbol. And this has 2 symbols. So this is not good. For this to have been a set, you should have had either only 1 symbol here, or one of these 2 cards should have had 3 symbols. Okay, makes sense? Okay, I hope it makes sense, because later on I'm gonna ask you questions. So, interesting fact, each pair of cards has a unique third card that completes the set. What does that mean? That if you already have 2 cards here, then you can find the last one that completes the set by figuring out what values each property has. So these 2 cards, they both have 1 symbol, right? So the third card should have also 1 symbol. Both are rhombuses, so the third card should also be a rhombus. Now they have different colors, so they all should have different colors. Okay, so I have red, I have green and I'm missing purple, so the third card should be purple. And what about the shadings? This is solid, this is open, so they differ in the shading. So the third one should also have the third missing shading, which is striped. Okay, so to sum up, it's one diamond, which is purple and striped. Okay. Clear enough? Hope so. And the game, as I said in the beginning, is deal 12 cards, deal a bunch of cards. And among these cards, you are looking for a valid set. Okay. Can you find a set?
There are 2 sets there.
There are 6.
6?
Yes. There are 6, so plenty of them. Anyone? Oh, you are first, Anjung.
The 3 purples with 3.
Okay. This one, this one, this one. Correct.
And then 2 green.
Wait, explain.
They have 1 stripe green, and fielding green, and blank green.
This one and this one. Okay, so does anybody understand why? First of all?
3 reds in the first row. 3 reds.
Wait, are we all on the same table though here? Do anybody understand why these are sets? Okay, so another one is this, this, and this, right?
Okay.
These are all easy ones. What about
Diagonal from the bottom.
diagonal? Where?
Left.
Yes.
Go diagonally.
This? No. No, this is not a set. Why?
Okay.
What?
The one above, green, the 2 greens above, and then.
This one?
No.
This one? Which one are you talking about?
Double green squiggly.
Okay.
Yeah.
This one.
Red ovals. No, or purple ovals.
Purple ovals and this one.
Yeah.
Okay, this one. Yes, correct. This is one of the most difficult, yeah. And there are more. So there is one here.
Okay.
There should be more. So this is taken, actually this is a puzzle that appears in the New York Times. And also in the set website, the game has a website and they put a daily puzzle, they call it the daily puzzle. So each day they put a set of 12 cards and there are always 6 cards and you are looking for these cards. You need to find all of them. Okay. Okay. Enough fun. So how did you do it? How did you find, if I'm given 12 cards and I'm looking for a set, what is like the most naive algorithm to find one?
Choose a pair and try? Or?
Yes. So basically the most naive way is look among all triples and see if one triple is a set. And slightly better is for each pair, seek among the rest of the cards if the third one is there. And why is that slightly better? Why did I say slightly better? Of course, if you do a sequential search among all the cards, then it's not better really. But you can have some kind of sorting of the cards. So the third search can happen in log n time. Log m time if m is the number of cards. So, okay, all these algorithms are either m choose 3, the first one, if m is the number of cards, right? Or m square log m, something like this. So, m to the 3 or m square log m, something like this. Okay? Generalization of the game that we considered is the following. So, instead of having 12 cards, you have m, and instead of having 4 attributes, 4 properties, you have n, and instead of each property having 3 values, there are k. Okay, and now for this generalization, the question that we ask is, does there exist a valid set now of k cards, because you have k different properties, such that k different values, such that all the values are either all the same or all values are all different. Okay. And of course, in the original game, as I said, m is 12, n is 4, and k is 3. And now we are going to formulate this problem as a hypergraph. And we're going to do the following. So we're going to have some n parts for each different attribute. And these are the values of each attribute. Okay, so let's say that if this is the color attribute, then this is red, this is green, and this is purple, for example. Or if this is the number attribute, then this is one number, this is two numbers, or this is three numbers, three items. Okay. So now a card, if you formulate the problem like this, a card is going to be a hyperedge that picks one value from each attribute. Okay, so this is a hypergraph, and this hyperedge is, for example, that for this attribute I have the first value, and for this attribute I have the second value, for the third attribute I have the first value, etc., etc. Okay, so in this sense, of course, I can have many cards, m cards. I have m cards in every instance of a game. And I'm seeking for k different hyperedges that have the property that they are either all different, like in this case, or all the same, that they all go through the same value. Okay, so I'm looking for k different hyperedges that have this property. And if you think about it a little bit, it might remind you of a very familiar problem, perfect and dimensional matching, which again is, I'm given a hypergraph and some hyperedges, but now what I'm looking is, if I have n dimensions like this and k different values, dimensions of size k in this hypergraph, what I'm looking is for a matching that goes through all different vertices exactly once. So in set I can have something like this, but in matching I cannot have this. It's all different. In set is kind of a variation of this, that I can have this case where hyperedges go all through one particular vertex. Okay. So as you can see, the two problems are very, very similar. And actually, we were not the first to observe this. These guys, Chowdhury et al., they had a manuscript in 2003, and they studied the complexity of this game. And they did this connection with n-dimensional matching. So through this connection, they were able to prove NP hardness for at least 3 different properties, attributes. So if you have up to three and more attributes, then the problem is NP complete from a connection to 3-dimensional matching, which is also NP complete. And for only 2 attributes, then it is easy to see here that you are, so if you have only 2, then you are either looking for a star, something like this, or for a perfect matching, which is known that in bipartite graphs is always in polynomial time. Okay, so this can be easily shown to be in P. K is unbounded. So K is this, N is this. K now is unbounded, and we are talking about N. So if N is 2, then the problem is in P. If N is larger than 2, then the problem is NP complete already from 3. Okay, and K is unbounded again. On the other hand, if K now is bounded, so if K is 2, I'm talking now only about 2 lines, in a sense, right? So many different attributes and only 2 different values. This problem is trivial. Why? So again, in a set, I'm looking for either the values being all different or all the same. So any 2 hyperedges have this property. They are either different or the same. Okay, so trivially this is any 2 hyperedges have this property. On the other hand, if k is a parameter, so for k equals 3, we already talked about this problem. It's a problem that we have 3 different values, and I already told you that there is an easy M choose 3 algorithm. Okay, just pick any 3 sets of cards and see if it's a set. So easily you can have an M choose K algorithm for K being a parameter. So this is an XP algorithm, but what about FPT? Can we do better than XP? We didn't know that, and we studied exactly this problem, and showed that this is W hard. And actually, what is even more interesting is that our reduction also holds for n-dimensional matching. So we showed that n-dimensional matching is also W hard parameterized by K, which is a new parameterization for n-dimensional matching. The only thing that was known before is this result by Fellows et al. Okay, so you don't know about parameterized complexity. Okay, so XP is a class. Okay, so this is a branch of complexity called parameterized complexity, where instead of having just one input, one parameter, the input size, you have some additional parameters. And you consider you consider some algorithms regarding to whether this parameter is small or not. So let's say if you have some algorithm that runs in time n to the k, when n is your input size and k is the parameter, then this is something good, because if k is fixed, is some very small constant, then this is actually polynomial time. On the other hand, if this k is bad, if this k is large, then this is something bad. Okay. An XP algorithm is an algorithm that runs in time n to the k. Now,
no, to the f of k.
Yes.
Yeah.
I'm just doing this really. So something that the exponent here is the exponent of n is something, some function of k. On the other hand, FPT is something that you have some function of k here times some polynomial of n. This is something much better than this, if you think about it, because if k is really small, let's say 3, then probably you really don't care. But if k is 10, then here you already have something like n to the 10, whereas here you have probably some constant 2 to the 10 times some polynomial, and this is something that usually we consider much better than this. So in general, what XP means is that if this parameter that we have is something moderately small, then this would be a polynomial time algorithm, a good algorithm. But even if this is like 10, most of the times it's not really good. It needs to be much smaller for this to be really good. You are seeking something that's called FPT, which is the parameter is not really in the exponent of n. You have some exponential function, but k does not appear here. So this is just a fixed polynomial. So yes, basically that's the distinction. Sorry, I thought that this was unknown. Make sense? Okay. So, okay, how many people from here haven't heard the word parameterized complexity before?
Haven't heard.
Haven't heard.
I haven't.
Okay. Okay. Yes, because I was about to talk about parameterized reductions, and I don't know how much sense that it makes, but anyway, I guess you all know about NP-completeness, though, right? Mm-hmm. So yes, if you know about NP-completeness, that's good news. So a parameterized reduction is a similar procedure like an NP-completeness reduction, NP hardness reduction, though you also have a parameter, as we said. In a parameterized problem, you also have a parameter. And you need to, you know already that some problems are hard for these parameterized classes that we have, like W hard. And starting from a W hard problem that you know already that is W hard, you make a reduction to a new problem that you want to show that it's hard. And what you need to make sure is that, of course, the reduction is in polynomial time or FPT time, what we call here FPT, this good thing. And also that the parameter, the new parameter that I create in my new parameterized problem is some function of the old parameter. And so it's really, really similar to an NP hardness reduction in this sense. And if you prove that, starting from a what considered hard problem, a new problem is also hard, reduce one problem to the other, then the new problem is also considered hard. And what we mean hard here is a problem that does not have something like this, okay, an FPT algorithm. So we have XP, which is something like a polynomial time algorithm given that K, this parameter K is fixed, a fixed constant. And inside XP we have this FPT that it's considered very, very nice, and we are happy when we have it. And it's something like this, as I said. And you also have these W hard problems, which are harder than, right? Somewhere here, I guess. And when you basically, when something is proven that it's W hard, then under some widely believed assumptions, it cannot have an FPT algorithm. Okay, so that's the story. It's similar to this NP-completeness theory. Okay, so what we actually proved is we started from a W hard problem, a well-known W hard problem, which is called K multicolored click, and we reduced this problem to our new problem. And the reduction is as follows. So let me first mention the problem. This K multicolored click problem is as follows. So you have a K-partite graph, and edges between parts. So of course you cannot have edges here. Edges only between the different parts. And you are looking for this graph has K parts. And what you are looking for is pick one vertex from each part such that you have a click. Okay, every vertex is connected with any other vertex that you picked. Okay, and the parameter is this size of the part, the number of parts, or the size of the clicks. The question is, does there exist a click of size K? And what I'm going to construct is, now we know that this problem is W hard, and what we are going to construct is an instance of n-dimensional matching that we want to prove that is NP hard, and the parameter is going to be the number of values. Okay, so we want the number of values the different number of values that we have to be some function of K, because a new parameter has to be a function of the old parameter. So what we are going to construct is K plus K choose two possible different values, one for each part and one for each pair of parts. And now dimensions are grouped in size n groups, like this. And we're going to construct some vertex hyperedges which look like this. So for each part, I'm going to make, for each vertex inside each part, I'm going to make some vertex hyperedge with some bumps. And the bumps are going to correspond to, we said that each of these are groups of size n, so they correspond to these vertices. And for each vertex, I'm going to have a bump here. Okay. And we're going to also construct some edge hyperedges, which are going to have bumps of the other, in the other direction. So in the edge hyperedges, I'm going to have bumps of this kind. So if I'm talking about this edge, from part I to part J, I go to this group, and I have a bump corresponding to this vertex, and now a bump corresponding to this vertex. Okay, so if you think about it a little bit, if you have a click in the original graph, if you have picked a vertex, two vertices from different parts connected by an edge, then this corresponds to two vertex hyperedges having bumps like this here, one here and one here, that are completely covered from the edge hyperedge. Okay, so the bumps match, and the whole thing is matching. And to make it a little bit more obvious, so let's say that I picked this vertex from part 1, my click. So from these groups corresponding to part 1, I have these bumps, these holes. There are k minus 1 altogether. And now if this corresponds to a click, then this vertex is going to be connected to part 2, to part 3, to part 4, etc. So this bump, all these bumps are going to be covered by the corresponding edge hyperedges. And there are k minus 1 in total. So one edge for each different part that they connect to. Of course, this is not like the whole formal proof, it's just some intuition of the argument, and I hope it's convincing enough. So that's a complete example. Probably you can get some more intuition if you look at it. So this is the click that I'm talking about, and here you can see the corresponding bumps and how they match together with the edges. This is the vertex hyperedges, and these are the edge hyperedges here. So that actually proves that this n-dimensional perfect matching problem, parameterized by the number of values, is FPT. So of course this is roughly k square size, the number of values, and it's a a function of the number of parts. So this completes the proof. And what about set? So we said that set is like n-dimensional matching, but not exactly. So in set, all values have to be different. In matching, all values have to be different. In set, some values can coincide. But here observe that from the construction, the constructed vertex hyperedges or edge hyperedges are really, you really have to create a matching. You cannot have all vertex and edge hyperedges going through one vertex. So that means that you have to have a matching. So the same reduction proves that set is also hard. Okay? Any questions so far? I hope I convinced you. So this is the first part of my talk. Now I'm going to talk about multi-round variation. So far, what we have been considering is we put some cards on the table and we are looking for one set. And once we find it, we are done. In this one, I'm looking for more sets. Okay. Of course, if I'm looking for coexisting sets, like in this case that I told you, we have 12 cards, there are 6 sets, find all of them. Then the same listing algorithm that works in time 12 choose 3s works for this case as well. Okay. Now the problem is what happens if I'm looking for disjoint sets. So one variation could be like find the maximum number of disjoint sets that are there. Okay, so in this case, this is a maximal set of disjoint valid sets, but with some more clever reasoning, we can do 3. Okay, so this is also 3 sets that I can pick independently. Okay. This seems like a more difficult problem than listing out all different 3 sets, and it's difficult even for k equals 3. And also the opposite goal, to find the minimum number of valid sets that destroy all existing sets, seems a bit hard. So this is 2 sets, a set of 2 sets that if I remove, then there are no sets left in the graph. Okay, so again the 2 problems. One is find the maximum number of sets that I can pick independently, one after the other, and the other one is find the minimum number of sets that I can pick and destroy all sets that are there. Okay. And again, I'm going to formulate this problem as a hypergraph, a different hypergraph than the first case. Again, I remind you that now I'm talking about 3 value sets. Okay, sets that have only I have only 3 different values for each property. So for this, for example, for this instance, I formed this hypergraph where each card is a vertex and each hyperedge is a set of cards that form a valid set. Okay. And again, these 2 problems that I'm talking about remind very much of well-known problems. Namely, one is the problem 3 set packing, which is exactly this. Given a hypergraph, find the maximum number of hyperedges that I can pick from this hypergraph. That yes. And the other one is the independent edge dominating set, which is find the minimum number of edges that I can pick and destroy all the other hyperedges. Okay. And of course, both problems that I'm talking about, both problems are restrictions of these well-known problems. And what we showed is that both restrictions remain hard. And we also showed some a parameterized algorithm for the second, where the parameter is the number of sets that you pick. Actually, this parameterized algorithm, our parameterized algorithm, works also for the general case, where you have general graphs and not set hypergraphs. And also, I want to mention that this problem, the first problem, was known to be FPT by these people. So, let me talk about the interesting fact that I said you in the very beginning about set, that for each 2 cards you can you have one third card that constitutes a set with the other 2. So this interesting fact, if you want to say it a bit more formally and mathematically, is really, okay, if I assign a value, if I assign to every value a number among 0, 1 and 2, because we have 3 values, then of course I have n different attributes and 3 values for each attribute. If I add corresponding values of a set of 3 cards that constitute a set together, then this is going to give me 0 mod 3. Why? So again, a card looks something like this. I don't know if you can see. So say 0, 1, 1, 0, 2, etc. And this is that for the first attribute the card has value 0, for the second attribute the card has value 1, etc. And if I pick 3 cards that constitute a set, corresponding coordinates, if you add them together, are going to give you 0 mod 3. And why is that? Basically, okay, so basically if you take corresponding coordinates, then they are going to be either all the same or all different. If they are all the same, then it's 3 times the value, so this is 0 mod 3. If they are all different, it's 0 plus 1 plus 2, it's again 0 mod 3. Okay, so this is an interesting property, this interesting fact described in math and explained a little bit more clearly if you talk about this set that I talked about in the very beginning and give particular values, like this is the shape, this is the color, this is the number of items, and this is the shading. You can see that I gave different values for its different attribute, and it's this property that holds. I don't want to stay more. And now, since we have this nice property, I can go on and give you the hardness of the second problem. So our reduction is from edge dominating set, which is NP hard, and we are going to prove that edge dominating set in hypergraphs, in set hypergraphs, is also NP hard. So I'm going to construct a set hypergraph starting from a graph and show that the sets that I create correspond to edges, basically. The cards that I create basically correspond to edges, and this is basically that the sets that I create correspond to edges. So if I remove edges from here, then I remove sets from the other graph. And namely, what I'm going to construct is some cards, one card for each vertex, that there is going to be n1 corresponding to the ID of the vertex. And I'm also going to construct some edge hyperedges that are going to create a set where I have an edge. Okay, so for this vertex and this vertex, I have n1 here and n1 in this place, so I'm going to put 2 2s in these places that there are 1s in these 2 cards, so that if I add all these together, then I have a set. So you can see, as I said, this is the trick that I'm doing. So taking this edge over here, there is n1 over here, n1 over here, and 2 2s that, with this nice property that I described, these constitute a set. And these are the only sets that I create. So, of course, it is really straightforward now to see that if I pick an edge in this graph, then this corresponds to a set here, and if I remove this set, then this is like dominating edges here. Okay. And again, if I pick yet another edge in my dominating set here, then this corresponded to this set, and if I pick it, then it's like dominating edges in the left graph. Okay. Good. So now I want to prove that this problem is also FPT if R, the number of sets that I'm picking, is a parameter. And what I actually promised you is that I'm going to prove this problem, that this problem is FPT for the more general independent edge dominating set problem on general three uniform hypergraphs. Let me remind you that set is again the same problem, but restricted to set hypergraphs. Okay, so at first what I want to say is that in order for this to happen, so in order for me to be able to pick R hyperedges so that they destroy all the other hyperedges in the graph, that means that this graph has to have a small heating set. Heating set, I remind you, is a set of vertices such that dominate all hyperedges, hit all hyperedges. Okay, so a hypergraph to have an independent edge dominating set of size R, it has to have a heating set of size 3, exactly 3R. Okay, pick the vertices inside the edges of the independent edge dominating set. If I don't have this, then I can say no. And the other interesting fact that I want to use is that I can actually list all the heating sets of size exactly 3R in FPT time. So this is really straightforward to do. So start from an empty heating set, and as long as you still have uncovered edges, pick an uncovered edge and pick all non-empty subsets of these vertices. There are 7 in total for every combination inside the hyperedge. And then once you pick these, put them in the heating set, and then remove all the covered edges, and continue like this. And if at some point you have a heating set that is larger than 3R, or if there are still uncovered edges, if all edges are covered, then either you found a heating set of size exactly 3R, so you put it in your list, or your heating set is of size larger than 3R, so you remove it, or your heating set is of size smaller than 3R, so again you remove it. So by doing this branching algorithm, you can find all heating sets of size exactly 3R, which are the ones that we're interested in FPT time. And once you do this, the algorithm really goes as follows: pick the next heating set in the list, size exactly 3R, and then take the induced subgraph in these 3R vertices, and check if there is a perfect three-dimensional matching in this one. And of course, this three-dimensional matching is an NP-hard problem if n is unbounded, but now this graph is all really bounded by R, so you can do this in time exponential in R, and you can show that the whole thing is FPT. And this is really a generalization of a technique by Fernau, who used edge dominating set and vertex cover, which is the equivalent of heating set in hypergraphs, and showed exactly the same algorithm. We generalized his trick. Okay, let me move on and talk about a slight variation of what I have been saying so far, a two-player variation of set. So the normal game is a game like there are many players, but it's like attack. So there are no turns. The player that finds first the set picks it, and this is a point for him or her. But in this game that we defined, it's a little bit more civilized. Players take turns. So the rules are, again, deal M cards, and there are 2 players taking turns picking valid sets. And once you select a set, you remove the cards, and then the other player picks a set, removes the cards, and continues like this. And the last player being able to pick a set is the winner. Okay, is it clear? So let's play. Okay, you start. Of course, you can see this is more difficult. That now you have to make a selection that somehow will restrict me, but also yes. Okay.
3 popper in the left bottom.
Which one?
3 poppers in the left hand bottom.
3. This, and this.
Yes.
Okay. Oh, you're gonna remove it. Okay.
Yes. Okay, and now it's my turn. So I'm going to pick this one. And now it's your turn. Yes. Sorry. Yes, there are no sets left. I'm the one to pick last, so I'm the winner of this game. Of course, there is a cheating involved here. You probably noticed. It can't be that I won so easily. Of course, I know the instance, so that was really easy for me. But actually I was not cheating totally. I mean, if you were careful enough, you could have won. So you can translate this instance to these 6 sets. I told you from the very beginning that there are 6 sets. And actually, if you picked either the yellow one or the green one, you could have won. Because this, if you pick the green one, this destroys the yellow, the brown, and the blue. And then there are 2 independent sets. And no matter what I do, then there is one left for you. And also the yellow has similar properties. So the yellow destroys the purple, the green, and the red. And then again, there are 2 independent sets. So I was cheating, but not entirely. So as you can see, this is a way more difficult problem than either the maximization or the minimization version that I was talking about. So now there are 2 conflicting goals, that you need to maximize your own sets that you pick, but you need to make me minimize the sets that I pick, and it's a little bit confusing what is the best strategy. So there is a similar game, well defined from the 70s, which is called arc-scales. And this is played on graphs, but you can also generalize it to be played in hypergraphs. And it goes like this. So players take turns picking edges now from the graph. And each time that you pick an edge, you remove the edge and all the neighboring edges. Okay. So which player has a winning strategy in this graph? So of course there is some symmetry here, as you can see. So this edge and this edge, this edge and this edge, and this edge and this edge should be equivalent to play, right? So for example, if I play this, then automatically I remove this edge, this edge, this edge, and this edge. Okay, so I'm left with this. Am I right? Yes. And then the second player can pick this one and delete this and this, and the second player wins. So this is not a good choice, and this is not a good choice either from symmetry. These 2 are not a good choice either, because if you pick this, then you delete this and this, and then the second player can pick this. Huh? No, this, sorry.
So the second player always wins?
Well,
No.
What if you choose a 4-6?
Exactly. This is the only edge that wins. So 4-6 wins. But there is only one, so you really need to consider the game a lot. So that means that the first player always wins, despite the fact that if you are not very careful, the second player is going to win. Okay, this is the problem with 2-player games, that you might have a strategy, but you need to be very careful. Okay, so arc-scales, as I said, is a really similar game. It's played on graphs, but if you consider it in hypergraphs, then it's exactly the same game actually. So the game arc-scales played on set hypergraphs, it's exactly the same game. And arc-scales on general graphs is a more general game that's played on general graphs. Okay, so I don't know if this makes much sense. So this is a hypergraph, and if I pick hyper edges in the sense that I told you, pick a hyper edge and then remove all hyper edges that share some vertex, then this game is exactly arc-scales and hypergraphs. Though in set hypergraphs, arc-scales is a more general game, but you can play in hypergraphs, 3 uniform hypergraphs that are not set hypergraphs. Okay. And what is known about this game? So, unfortunately, not much. So the complexity of arc-scales is unknown. It's not known if it's hard or not. Of course, that means that the complexity of 3 uniform general hypergraphs is also unknown. If this was shown hard, then this would be hard automatically. And the only thing that we do know is that it's piecewise hard on general hypergraphs. So if I have unbounded size hyperedges, then this was shown to be piecewise hard, and actually quite recently in 2013. And we do know, we do have some very old results about a similar game which is called node scales. So node scales, where instead of edges I pick vertices, is already known to be piecewise hard, and AW star hard, parameterized by the number of rounds played, so the short game. And our results is that, of course, the reduction that I showed you from this reduction that I showed you here can generalize. This can generalize arc scales, and this can generalize the two-player set. So this actually shows that the two-player set is at least as hard as arc scales. Of course, this is not very helpful because we don't know the complexity of arc scales. And where am I here? And we also showed that this game parameterized by the number of rounds that you play is FPT. Though I'm not going to show you this proof because I'm almost out of time, I guess. And it was a bit complicated to describe. And also what I want to say about this algorithm is that it works on a bit slightly more general three uniform hypergraphs that have this nice property of set that two vertices can be a hyperedge in a hyperedge with only 1/3. Okay, so as I said, for the set game, two cards can be a set with a unique third one. Okay, so if you have this property, then you can have this nice FPT algorithm for arc scales in general three uniform hypergraphs with this property, but we don't really know if it is FPT. The arc scales in more general three uniform hypergraphs is FPT, parameterized by the number of rounds. And also something else that is left open is, as I told you, the complexity of arc scales and the complexity of these two-player games. So mostly open questions, mostly for the two-player games. The one and multi-round variations are mostly covered by what we proved and what was already known. So to conclude, what I showed you today is that it's really, really interesting to play games in terms of computational complexity, because this game turned out to be really similar to many well-known games, and by studying this game we were able to show interesting results about well-known combinatorial games. So this is not a completely worthless field of study. And what we established is connections with multidimensional matching, set packing, edge dominating set, and this well-known arc scales game. And I hope you enjoyed. And if you want to know more, this appeared in Latin. This paper appeared in Latin 2014, and also there is an archive version, which is a bit more lengthy. Thank you very much.